let's look at some limiter and clamper circuits here. So in the first few problems, we're asked to find what the V out would look like. So let's talk about what happens with number 33 here. We've got the input varying from 10 volts to a negative 10 volts. And the diode is pointed in this downward direction. So when it's on, what we should see is that it is conducting current in this direction. And when it does, we should see a drop of 0.7. So when that's going to happen is in this portion of the waveform here. So when it's greater than 0.7, we should see it conducting. When it's less than 0.7, the diode should be off, which will make an open circuit. So what does that look like in terms of the output? On the positive going side, we're going to see that that signal rise to 0.7, and then it's just going to flatten out at 0.7 because once this diode is on, V out is in parallel with the diode, so it can't be anything more than 0.7 at that point. We're going to see the rest of the voltage drop across the 1K ohm resistor. But across the diode, which is where the output of the output voltage is, that would be limited to 0.7 volts. And that's why they call this a limiter, because it's going to limit it to not going above the 0.7. Now, when it's below 0.7 and the diode is off, that's going to create an open circuit between the input and the output. So the output at that point is simply going to be whatever the input was. So it should be the negative 10 volts on the other side. So anything up to 0.7 is exactly what the input looks like. So over here, and then anything below that would be on the output. Okay, let's look at number 36A. Again, we're going to look at what the output would look like. Now, when our voltage climbs above 0.7, and I didn't mark that this is the output over here. When our input climbs above the 0.7, our diode will, of course, be conducting current, and we'll see that 0.7, which again is in parallel with V out. So on that positive going side, again, we're going to see it limit that voltage to 0.7. Now, what about on the other? What about on the other side? When it's below 0.7, let me see if I can. When it's below 0.7 and our diode is off or open, think about what's going to happen. We're going to have current. Remember, that's on this negative side predominantly. So we're going to have that current going through our 1K ohm resistor over here and through a second 1K ohm resistor over here until it gets back to where it started. So that is a voltage divider. So we're going to see 5 volts across two 1K ohm resistors. So there's a couple things you can do here. We can find the current and then multiply the current by the 1K ohm resistor. Or if you recognize that this is a voltage divider, we can just say that V out will be 1K over 1K plus 1K times Vn. And of course it's going to be that negative. So basically that is 1/2 of Vn, and if you're looking at the peak, that is minus 5 volts on that negative side. So that would be minus 2.5 volts. So on the negative side, we're only going to reach a peak of negative 2.5 volts. So the output's only going to be half of what the input is, anything below the 0.7, and that's going to be our output for that circuit. All right, so let's move on to B. Here we have a signal that's varying from 10 volts to negative 10 volts, and we have the diode. Actually, it looks like we've got this limiter circuit biased as well. So biasing just means that we included a DC source in the same path as the diode. That's going to further change the limiting voltage that we're looking at here. So in order to turn on this diode, we need the anode side to be biased 0.7 of a volt more than the cathode side. So in order to turn that on, let's say this is ground down here, we're going to need to see at least 3.7 volts up here, because remember, right at this point we have 3 volts. So to have the anode biased 0.7 more than the cathode, we would have to actually have that at 3.7. So pretty much anything above the 3.7 mark over here in that input would turn the diode on, and then the output is simply in parallel with that. So if this is the output over here, we're just going to let that climb up to about 3.7, and that's where we're going to limit our voltage. Now on the other side, when this is below 3.7 volts, we're just going to have whatever is on the input. Now we do also still have a voltage divider here. When this middle branch, when this is off, we still have a voltage divider. However, the voltage out is going to be across a 1 mega ohm resistor, while the other resistor is only 56 ohms. So RL is so much larger than R1 that pretty much all of the voltage is going to drop across the 1 mega ohm resistor. And you could actually work that out using the voltage divider rule if you want. It comes out to about 9.999, something like that. So we're just going to say 10 volts at that point. And that would be the output of that limiter circuit. So basically it's the same as the input, except we're going to limit everything that's above 3.7 to stay at that 3.7 level. Okay, and now for part C, this time we have a signal that's varying between 200 volts and negative 200 volts. So when this diode is on, is going to be in the negative portion of our waveform. And let's kind of determine what the voltage would have to be in order to have that on. So let's say this is ground down here. We have a bias voltage that is going to drop 50 volts. So at this point we have negative 50 volts. Let me rewrite that, it's a little messy. Negative 50 volts right here. And then when this is on, we're going to drop another 0.7 from the anode side to the cathode side. So up here we would have to be at negative 50.7 volts or lower for that diode to be on. And when the diode's on, our output would just read whatever is across that branch, which would be negative 50.7. So what we're going to see is on the negative side, we're going to limit this to negative 50.7. And then on the positive side, well, actually anything above, let me change the color of this. anything above that's greater than the negative 50.7 is going to make that diode off. And at that point, we would just see the voltage across RL. Now, in this case, when the diode is off here, and we have current coming through this way through RL and R1, that does make a voltage divider again. So let's look at what that would be at the peak of 200 volts. So V out would be the 680 over the sum of 680 plus 100. That's the total resistance in that pathway. Times, let's just do the peak, okay, because everything else is going to just be offset from that. And so what that gives us is about 174.36 volts, or 174 volts, something like that. So we are going to have our positive peak here, but it's only going to go to about 174 and not to the entire 200, because we do have a voltage divider there. And the other portion, that other 25 volts, will be dropped across R1 when this diode is off. Okay. So again, when you're looking at limiter circuits, you really want to look at what causes the diode to be on, and it depends on where you take the output as to what the output signal is going to look like, or where the limiting factor would be. Okay, so let's look at number 37, part A. Now this time we have, for our limiter circuit, we have two diodes, one in that upward direction and one in the downward direction. So let's look at what that would do. So in the in this portion of our input, the positive portion, we would be turning on D2. It would be forward biased, and D1 would be off. So what would V out be? It would be limited to 0.7 volts across this diode because it's in parallel with the diode. Okay, so in that forward direction, we're going to limit that to a positive 0.7 volts. And let's talk about what happens in the negative direction. Let's go back to a different color here. So in the negative direction, now, let's see if I can get this out of here without losing everything. So that's D1. So when we're in that negative portion, we're actually forward biasing D1, and then D2 is actually off. And we will see this drop of 0.7 volts. So NV out is still in parallel with D1. So then we would see it limiting the other portion of our output to negative 0.7. So that's what the two diodes in parallel but in different directions would do. Okay. Okay, so D2 here. Okay, and so then what would the, no, 37B is exactly the same thing. They've just kind of flipped over the two diodes, so I did not include that one. So now we want to talk about what the current is through either of the diodes. So if we have 0.7 volts across D1, no, in D2, and D1 is open, not conducting any current, then the rest of the 30 volts in that forward direction would be dropped across the 2.2 k ohm resistor. So let me show you what I mean. If this is on and we're conducting current here, and we have this drop of 0.7 volts here, we would have to, at the positive peak, that means we would have 29.3 volts across R. And when we're asked about what the peak current would be, we're just interested in the peak voltage, because anything below that would have a smaller current. So what would that current be? It would be the same current as the current through the resistor, which would be VR over R, or 29.3 divided by 2.2 k ohms of resistance. So that would give us about 13.3 milliamps of current. So that's going to be the biggest current that we would have through D2. And it also works the same way through D1, because the negative peak is the same, the negative 30, would just be in the opposite direction, but it would still be the same current. Okay, so let's look at number 40. This is another limiter circuit. And here we've got, again, we are varying our input from 30 volts to negative 30 volts. And let's look at what condition would make our diode on for this circuit. So again, if we've got, we have a 12 volt bias here on the anode side of the diode. And so the anode would need to be at least 0.7 more than on the cathode side. So if we take that 12 and we subtract 0.7, as long as we have 11.3 volts or smaller for our waveform up here, that would turn on the diode. So anything that's smaller than 11.3 would limit our V out to 11.3. So basically that's just for this yellow part of the input, and well, anything that's smaller, sorry. Actually, all of this is smaller as well. So anything smaller would limit the V out to the 12 minus 0.7 or 11.3. And then anything above, let's look at where that would be. Anything above, right up here, would turn off the diode, and it would just pass straight through to the output. So what we've got is something kind of interesting here. Anything above the 11.3 would pass right through, but anything below would remain at 11.3 volts. So that's a different kind of a limiter. It's limiting a good portion of the actual waveform. And then for C, it's pretty much the same circuit, but we've turned around the diode and the biasing voltage there as well. So let's look at what happens here. So again, look at the condition that would turn on the diode. So the diode would be on as long as the anode to the cathode has a 0.7 volt difference to get over that barrier potential. So if we've got ground down here, we're going to drop 12 volts, so this would be at negative 12, and then we're going to add the 0.7 as we go up to this point right here. So negative 12 plus 0.7 would be negative 11.3. So what we're saying is anything greater than 11.3 here, anything greater than 11.3 is going to turn on the diode, and it's going to limit the output to that negative 11.3. So what is greater than 11.3? Pretty much anything on this waveform that's greater than 11.3. Whereas for the rest of the waveform, it's just going to pass through because the diode will be off and it'll be open and it'll pass whatever Vn is to the output. So we have pretty much the opposite effect here, where we have a peak of negative 30 volts, but it limits the rest of the voltage to not go above that negative 11.3 there. Okay, so those were the limiters. Now we're going to look at DC restorers, or clamper circuits as they're called. So again, we're going to look at what would the output voltage be. Now, we're not looking at values of resistors and values of capacitors. We're just assuming that the resistor is large enough to make that discharging phase very small, very long, I'm sorry. Make that slower than the charging, okay? As long as that's the case, we don't have to worry too much about the difference there. We're assuming when the capacitor is charging, it's charging up instantaneously or very quickly, and when it's discharging, it's slowly enough that we don't have to account for that. Okay, so let's talk about the clamper circuit and what's really happening here. When the diode is forward biased and it is on, then our capacitor will be charging, and it's going to charge very quickly. We assume that it's going to be very fast. So what is happening is we've got this drop of 0.7 here, and it's going to be charging up whenever we're in this positive region here above 0.7. So let's just take a look at the positive 4 volt. So at the peak, what would our cap be charging to? If we've got 0.7 across the diode, the rest of that 4 volts is going to be what the cap charges to. So it's going to charge up to 3.3 volts. So in the charging phase, when our diode is on, so when the diode is on, again in that early positive phase of our cycle, what that's going to do is it's going to limit we're going to see a limit of up to 7/10 of a volt on that positive side. And then what happens when we go to the opposite direction, this is where it gets really interesting. In the opposite direction, when we're no longer conducting current through our diode, the cap is still charged, okay? So let's just look over here. So at -4, what we have is positive to negative 4 volts over here, if we're looking at this peak right here. And then V out is going to be, we'll use Kirchhoff's voltage law to look at what V out would be. Remember, the diode is off now, so all of the voltage is going to be across VR. So KVL would tell us, if we go in this direction here and V out is like this, we've got a -4, minus 3.3 volts, minus V out has to equal 0. So that means our V out would be -7.3 volts. So over here, we're going to see a drop of -7.3 volts for the output. Now, the interesting thing, again, about clamper circuits is that whatever this envelope is, right, we have an 8 volts peak to peak here. I think I didn't give myself enough room here. Whatever this is right here, we've got 8 volts here. We're going to have that same window on the output. So minus 7.3, well, so we've got 7.3 on one side. I don't want to confuse you too much with the pluses and minuses, but we've got a 7.3 displacement on this side plus a 0.7 displacement on the other side, and there's our 8 volts. So for a clamper circuit, you still have the 8 volts, and that's kind of a good way to look back and make sure that you didn't make a mistake with your output. You should still have the same displacement. For the next problem, for instance, at the end for this clamper circuit, we should still have 30 volts across from the positive peak to the negative peak, whatever it ends up being. Okay, so let's look at the output for circuit B. So when is our diode going to be on? First of all, it's going to be on in the negative portion because in the positive portion, this diode would be reverse biased, but in the negative portion of the waveform, the diode is forward biased. So it would be on, and we would see a drop of a drop of 0.7 across there, and it's going to be negative 0.7. So when it's on, we should see this negative 0.7 volt peak, as V out is just whatever the voltage is across the diode. And then when and what's happening at that point is we're charging up our capacitor to whatever's left over. Okay, so we should have 14.3 volts there. So in the opposite direction, when the diode is then off because it's reverse biased, that's going to be in the other portion of the input, which is the positive portion. And at that point, we would have a peak of 15 volts. So again, KVL, the equation would be plus 15, if we're looking in this direction, plus 15 plus 14.3, and then minus V out is equal to 0. So moving V out to the other side means we would have 19.3, oh, I didn't do that right, 29.3, 29.3 volts. So that means we'd have the 0.7 over here, and then the 29.3 volt peak over here. Okay, and so that's what our output would look like for that. Now let's look at two that have square waves. Square waves are actually a bit easier to visualize, but let's see. So again, but it's all the same. So we're looking at when is the diode on. So in this case, the diode would be forward biased when we have the positive 8 volt portion of the square wave over here, and at that point we would have 0.7 on the output. So this would be a positive peak of 0.7, and while that's happening, we are charging up the cap with whatever's left over. So that would be 7.3 volts. Then when we get to the other portion, the negative portion of this square wave, that would turn our diode off. Where we have 8 volts here. Again, looking at our KVL to determine what would be the voltage on the output, we would have -8 minus 7.3 minus V out equals 0, which means V out would be minus 15.3. So over here, we would have a negative 15.3 volt negative square portion of the wave. And again, let me point out that from 0.7 to negative 15.3 is a swing of 16 volts, which is the same as our input. If it's not, you might want to recheck what you've done. Okay, next problem. So we've got the diode turned around the opposite way in a square wave alternating from 1 volt to negative 1 volt. So remember, when our diode is on, would be in this negative portion here. I was trying to get the in this negative portion here, because what we need is to have a drop of 0.7 volts here. So if this is ground, we need this to be negative 0.7 or lower. So negative 1 would turn the diode on, which means we would have an output of 0.7 at that point. Okay. So in that portion, we would have an output of negative 0.7. And then what's happening at that point is we're also charging this capacitor to whatever is left, and that's just 0.3 because we've only got 1 volt to work with. So if we've got 0.7 across the diode to turn it on, we're only going to charge that cap up to 0.3. So then when we turn to the other direction, so we've got our 1 volt here. Then we're going to use our Kirchhoff's voltage law to figure out what would be on the output, because again, at that point the diode's off. Okay, so KVL, we'd have +1 plus 0.3 minus V out equals 0. So V out would be 1.3 volts. Okay, so on the positive portion, it'd be 1.3 volts. And again, that gives that swing that I was mentioning before of a total of 2 volts, which is what we had on the input as well. Okay, so those are our clamper circuits. Now, the last thing I wanted to go over was some troubleshooting. We're going to figure out for these next circuits if they're operating properly based on the voltmeter reading. So let's look at 48A. We have a reading across the diode of 25 volts. Now, that's in the forward direction, because we've got our plus here and our minus here. So it should read, if this is working correctly, we should read 0.7 volts or whatever the barrier potential is of the actual diode. And since it's 25, that tells me that it's not working properly. Or it's reverse bias. So we would look at what's going on at the input, and at the input we have 50 volts with the positive terminal connected to closer to where the anode is, and the negative terminal connecting to closer to where the cathode is, which should be forward bias, so it should actually be 0.7. So the fact that we're reading 25 volts, what I would think is, if this is open, let's say this is open over here, then we would have no current through our 10K ohm resistor over here. If we had current through here, the two 10K ohm resistors would split that 50 volts in half. So we would have 25 volts here, and we would have 25 volts here. And since the digital multimeter is actually reading 25 volts, it looks like that's correct over here. So in this case, it appears that the diode is open, and that needs to be replaced. Okay, so that is a malfunction. Okay, let's look at our next circuit and see how the diode is operating here. Again, we see that we should, if this diode were on, we would have a 0.7 volt drop here. And instead we have a 15 volt drop. So that's either it's not forward biased and it's an open circuit because it's supposed to be, or it is forward biased and it's not working properly. So let's think about this. Again, look at your source. We've got the positive terminal going toward the anode side, which should be positively biased, which should be connected to the positive terminal. And the negative of the voltage source is connected to the cathode, so it should be forward biased. So it should have a drop of 0.7, and the fact that it doesn't tells me that something's wrong. If this were open, then what would my voltage be across here? If it were open, then there would be no current through the resistors. So we really would have 15 volts there if the diode were open. So again, looks like the diode's open and needs to be replaced, which is, of course, a malfunction. Okay, let's look at C and see what's going on here. All right, so here it looks like we've got our 5 volts here. Now, interestingly enough, our negative side of the 5 volts is connected to the anode, which for it to be on should actually be the positive side going to that, and the positive side of the 5 volts is closer to the cathode. So that really, it should be reversed biased. Okay, so it should be reverse biased based on the circuit diagram, which means that we should have I should be 0, right? However, you notice that we have a voltage across here, which means that we do have a voltage drop across our resistors, and they are splitting the voltage in half, which they should do if we have all of our current flowing through there. However, we really shouldn't have that current flowing through through this diode in that direction. I'm sorry, our conventional current direction would actually be this way, and current should not be going that direction through that diode, however it is. So what that tells me is that our diode in this case is shorted. Okay, and that's another thing that could happen with a diode. It can be open or it can be shorted. So I think it is shorted, which again is a malfunction. It should not work that way. In this case, this diode should be preventing the current from flowing through those resistors, and it is not. Okay, so let's look at our final circuit here. So we've got the positive side. Let's see, did I draw this one right? Positive side. Okay, the positive side is connected to the cathode side, and the negative is connected to the anode side. So our source is trying to create a current in this direction, and our diode should stop that current. Okay, it's reverse bias, so there should be I equals 0, right? If it's working properly. Now, our voltmeter is actually measuring 0 volts, which tells me that we have 0 current through that resistor. So in this case, it actually looks like the diode is working properly, as it's expected. Okay, because in the reverse bias, it should not be allowing any current to flow through that. And those are some of our limiter and clamper circuits